variable selection method. So we want to find out, so there's a lot of bunch of the variable, but I don't want to use all of them. If you find out the one variable that is highly correlated to the other, so that's a collinearity. You can calculate the VIF value, and high VIF value, you can drop it. However, in general, if we have a bunch of the variable, you don't want to develop the complicated regression model with like 100 variables. So actually, I experienced when I was a postdoc, and then my project was trying to find out the patient will accept the organ for the organ transplant. There is like hundreds of the variable. So, but we don't want to develop the model using the hundreds of variables. So we choose about 50 variables, but 50 is still a lot, right? However, since we have several hundreds, so we don't want to create the model using the 100 variable. So how can we select which variable should we use? Which variable should we drop? This is what I'm talking about, is a variable selection method. First one is a forward selection. Forward selection is starting from the no variable at all. No variable at all is you have only the intersection. So starting point is the y equals interception. It's not an interception. This will be like a mean value, mean of y. But that's the best. If you have to use only one number, what one number should be your estimation? That should be the mean, right? Without any x. And now you are adding x one by one, right? So we will talk about the forward selection. The forward selection is you just add the variable, and then backward elimination is you include everything you have, and then you drop some of them. Stepwise is sometimes you add, sometimes you drop, and then moving back and forth. And all possible regression is it calculating the regression of all possible combination. One variable, two variable, but two variable also there's so many different two variables, right? If you have a 10 variable, you can have a 10C2. That's about 45 different combinations, right? You can have a 3 variable. So really, there's really a lot of the possible combination of the variable, and then you try all of them, and then you choose best one. So here the best is also kind of the tricky part, but you have to decide which will be the criteria, which one you should use. Or just R is the best, are the criteria, or the p-value. So that's the most common criteria when we do the forward or backward stepwise. We use just R square or p-value. That's we have a lot of different things, or the p-value. This is the two most commonly used the criteria. Should we add this variable or not, or should we eliminate this variable or not? So to do this, you can actually download this OLSRR package. Once you have this one, you can do all these four things. So what is adjust schedule or adjust R square? We already seen this one. Actually, I copied this slide from the simple linear regression. But this one, you can consider this is the R square that penalize. As you can see here, the K is in here. So if K increase, this one decrease, right? So when k increase, the denominator will decrease. Denominator decrease, this calculation will increase. So 1 minus will decrease. So this is like a k, when k increase, actually r square will decrease, right? So what would be the effect is when you have a more data, more variable, it will penalize. It will give us some kind of penalty. So when we why we use just the r is r square is increased whenever you add the variable, even though it's no, the worst case is what? Worst case is r square doesn't increase at all, because if you bring the totally unrelated variable here, what you can get is the beta k can be 0. Yeah, I think that's totally wrong. It doesn't have anything related to our y. Then you can have a 0. Then that doesn't affect at all. Then your r square will not increase. That's the worst case. So whenever you, even though you bring the totally unrelated the predictable variable here, still your r square will be increased just a little bit. So if you just look at the r square, you just put it in like thousands of the decision, the predictable variable, your r square will be just a little bit, and it keep going up. So you cannot tell, so what is the better? Did you get a r square pretty high only because you have like thousands of variable? That's not a good model. So that's why we use r square here, adjusted r square. Adjusted r square penalize a lot of the predictable variable. So when you see the adjusted r increase, which means even though I add the new variable, so I got penalized because I increased the more predictable variable, but my r square increased more than that. Then adjusted r will go up. So if you bring the really good variable, it has a high predictable power, then by adding the new variable, you got penalized by, as you can see here, the k increase, this decrease, and this increase, this part increase, and then as a total, r adjusted r square decrease. But if that variable was pretty good, then you will have a pretty high r. So your r square increase will be greater than the effect of this penalty. Then your adjusted r square will goes up. So whenever you see r square goes up by adding the one new variable, that's may or may not good, because the even though your new variable doesn't have a high predictable power, r square will go up anyway. So I want to measure. So my new variable will increase my r square, but that's a significantly more by overcome the penalty of the adjusted r square. So whenever you see the r square, adjusted r square going up, which means your new adding variable that bring the enough the value to the your y value. So that's why the adjusted r square is useful when you compare the two different models, especially when they have a different number of variables, right? So one model has like a three axis, 3 variable, and the other model is a 5 variable. They have a different r square. Then how can we tell which one is better? Then adjusted r can be the one measure to see which one is better.